sometimes Providence just takes care of things. And I think the next presentation that we have is such a good follow-up to what we just heard, because we're going to get a little bit more granular into the use of camera technology and AI technology to be able to really define animal identification and perhaps start implementing some phenotyping based on this technology. So I'd like to welcome Mokah Shmigelsky from OneCup AI. They're a Canadian-based company that we're really proud to be working with to develop this.
Good morning, everybody. Thank you for having me here. Thank you to Kajal and Miles and the CAA and BIF for inviting us to speak today. And it was very serendipitous that we are speaking after Dr. Steibel, because what I'm going to show you is a lot of what he talked about, but how we've implemented those technologies into a production system on farm and in feedlots. So my name again is Mokah. I'm the CEO and co-founder of OneCup AI, where we've designed AI technology using computer vision. And our AI's name is Betsy, which stands for Bovine Expert Tracking and Surveillance. So this is basically how Betsy works. Oh, this one's a little stoppy and goey. So this is a lot of what Dr. Steibel was talking about. So we're using a lot of the same types of models in our AI pipeline to create the different data points that we want to use for our AI pipeline and for our tracking system within a production system on farm or in a feedlot. As you can see, these are just 5 of the models in our pipeline. And as we go through this talk, I'll show you a little bit more about how many models that we use in our pipeline and how each of those models helps us to come to the end result that we look for. As we start, let me go back here. As we started our journey several years ago, it all began on a farm in southern Alberta with my family members who raise Angus out in southern Saskatchewan. And what we did was we were sitting around a campfire and discussing some of the pain points in the livestock industry. And you guys all know the pain points in the industry, but the number one key component that my cousin identified was identification, permanent traceable identification. And that's where the whole system began. That's where we started from. So the visual identification was our key technology stack. And that was our first developed product. But as we went through the development process, we discovered that there was a lot of different things on farm that producers didn't have access to, because many of these processes, as you know, are very manual. It takes somebody to be on farm and actually visualize those animals to see what's going on. This is just 8 of the original propositions that added value to the farm. And as you can see, visual ID is the number 1. So in the beef and dairy cattle industry, the use cases that were identified to us from our producers and our beta sites were calving, shipping and tracking, estrus and breeding, and feed tracking. So I want to talk a little bit about the calving detection model. So after we identify the animal, we go through the process of identifying the different body parts, as you saw in the very first video slide. And then we wanted to identify different behaviors so that we could alert producers what was going on with their animals. The pre-calving activity, the birth of the animal, and the calf after it was born, and the colostrum uptake. As we developed these models and started to collect data for these, we found a number of challenges as we were going along. And the number one challenge was data. So in creating computer vision models, you need to have a robust data set. And like the previous speaker identified, having all of that data has to be annotated as well. And that's a very human part of computer vision right now. So our first idea was that we could identify all of these different things: calving activity, so contractions, changes in movement, changes in feed and water intake, and then tracking the contractions over time. And in real time, that was a very big challenge because we not only needed to collect that data, but then we needed to hand annotate it as well. So one of the things that cows like to do is when they're in labor, they like to walk away from the herd. They like to go away from where our cameras are set up. And even if they are having contractions in front of the cameras, what we found was they were not always facing the right way. So we had to try and tweak and figure out exactly how we were going to get that data and have the animals in the proper orientation for annotation and then training and validation. So then we also were going into sort of the confined animal space and feedlots and dairies, swine barns, and these sorts of things. The things that we were looking for were lameness, whether or not we could use computer vision to do BCS scoring, growth tracking, and then illness detection at an earlier time period. And again, when we were collecting data for these models, what we were finding was illness detection, being able to detect symptoms like a runny nose, a cough, lethargy, all of those types of things. We had to collect a lot of data specific to that particular symptom. And so when we were going through the development of some of these models, we decided that rather than track individual symptoms, we were going to track what the animal's behavior was. And since we know the identification of the animal, we can track their behavior over time, as well as behavior, how it relates to the other animals in the herd. And so we can track things like water intake, how many times they're going to the water bowl. And by that, we can also track if they aren't going to the water bowl one day as often as they normally do, or if they're outside of the average of the herd. This is how our producers experience their user portal. So this is our custom video player where you can visualize your herd through Betsy's lens. You can turn on and off all of the different models on the right-hand side there. You can select different animal cards on the left as well. You can also select animals within the frame of video to find out more information on those animals. This was a way that we used our Betsy system to show producers what the value could be to them and how they could visualize their animals. Sorry. And then this is how our user interface looks. And so what we found with producers is they want to have all of this information, but they also want to have it in an easy to digest manner. So they don't want to have to break down the spreadsheets. They don't want to have to analyze their own data. And so what we do for them is we give it to them in a nice graphical format. We show them the output and behavior changes in their animals, any alerts. So on the left-hand side, that's what we do for calving is when we identify an animal that's in labor, we text the producer or email them and let them know, combined with an image of the animal in question, and then they can make the choice to go out and check their animal at that point. So this is how Betsy's brain works. This is essentially her entire neural network. And so as you can see, the level 1 detector is an animal detector. So it's similar to a YOLO model where we identify the different animals in the scene, but we can also identify humans, cars, trucks. And we found that we needed to create a more robust model to detect the different animals in the scene. So we've done a custom AI pipeline so that we can create the model accuracy that we need for that level 1 detector or the level 0 detector. As we go into level 1, those are the bounding boxes. So that depicts the head, the feet, the knees, the tail, the entire body of the animal. And that's how we pull out the relevant pixels that we are using in the future models to do the different things like the identification or the 4th level classifiers where we want to be looking at a specific body part of the animal. We also have a key point model as shown before. So our key point model is 52 key points. We found that that was the best to give us the most pixel data that we wanted. And within our key point model, we also have built in the angles as well. So that gives us the data that can allow for us to show things like limping, changes in gait, and that sort of thing. And the level 3 is our identification system. And so that's where we can pair the final output data, those time series and level 4 instance data back to an individual animal. So what we do is we use visual identification similar to what your phone does, like Face ID, but we use the entire body of the animal, 512 points on the animal to identify each animal. And then we also read the drop tag, the management tag that each animal has, and we pair those two identifications together. The management tag is the ground truth for the animals, so that allows us to have 2 identities for every animal in our system. We don't read EID tags right now, but we do have a space within our system to manually input the EID tags. So then at that point, you would have permanent traceability throughout your food value chain. The level 4 instance is obviously what most of our producers care about. And so that's where we're getting into the nitty-gritty of all of the different behavior changes, growth changes, and nutrition. Here's an example of our level 1 bounding box detector. So as you can see, it works on cattle, horses, dogs, any species of animal that you might want to be monitoring. And here's some examples of our 52 key point model. So on the upper left-hand side, you can see that that animal looks a bit like a video game cow. We also use a lot of synthetic data to create data that is precision annotated right out the gate. And it allows us to create a more robust data set so that we can create things that you might not catch in the real world. And then this is an example of our level 3 accuracy for our OCR. So this is the tag read. And this is a study that we did with Lakeland College 2 years ago. My graph is a little squished, but we can get up to 99% accuracy on the tag read with 200 by 200 pixels size for the ear tag. This is a heat map that shows what the different body parts of the animal are being used for in the identification. So it's not a temperature read, but more so we're feeding Betsy information and we're allowing her to determine what the differences in the animals are. And so what we wanted to do was have her show us how she was determining the different features of each individual animal. And in this case, this calf 505, those are the 3 points that differentiated it from the rest of the animals in its group. This was some of our preliminary calving detection models. And throughout this process, we discovered that, so we were using the tail and the angle at which the tail was going out for contractions. And excuse me. One of the funny side effects of using the tail for contraction identification is that a contraction also looks very similar to a bathroom break. And so what we had to do was try to figure out the difference in what a tail looks like when having a contraction and what a tail looks like when they're going to the toilet. Here we were just asking Betsy to make sure that she was actually looking at the right parts of the body of the animal to determine what its activity classifier was, because again, we feed it the information and the labeled data, but we want to make sure that she isn't misclassifying things like trees as a laying down animal. As you can see, she's identified the bottom of the laying down animal as that's what's identified as that animal is laying down versus the second image where the legs are clearly outstretched and walking. So then we had a relationship begin with Codgill and Miles at the CAA, and they identified for us that computer vision could be a very interesting way to identify and accurately track phenotypes in the field. So as you know, phenotypes are very manually tracked right now, and there's a lot of room for human error. And so we started working with the CAA a couple of years ago in determining different phenotypes. And what they did for us was identify which phenotypes were of the highest importance. So we started with hooves and claws and teats and udders. And so here, what we did was use the CAA's scoring metric and try to figure out how we could show Betsy the differences between the scoring from 1 to 9. And you can see 4 scores over there. And so what we did was use our key point model and add additional points to the hoofs and the claws to compute the angle. So in theory, the ratio works out well, but in practice, there is some work to be done. So essentially, we did the same thing with the claw set and computed the ratio using those points in the middle of the claw. And then we also created a 3D visual so that not only could we use it for additional data points in our training of the model, but we could also use it for education purposes in the industry for producers. We took a similar approach to teats and udders, where we identified the 2 polygons on the right there, and we were going to do it on a ratio scale as well. We also created 3D models for perfect teats and udder scores as well. And here you can see the ideal foot, claw, and teat and udder score of 5. So what we were finding was the ones that were 4, 5, and 6 were quite hard for the system to pick out the differences because they were quite subtle. But then what we also found was this is what it looks like in practice. Now, these cows are pretty clean. Their feet are nice and tidy. They have a hard surface that they're standing on. So we get good ratios. We can get a good analysis of their foot and claw score. But in practice, this is not what cows look like in the field. And so we were finding that mud on the foot, walking through grass, all of those things affected our accuracy and our results, as well as the fact that nobody keeps the 1s, nobody keeps the 9s on their farm. And so we were finding that our data sets were not robust enough to be able to pick out those extreme cases. And so we need to collect more data, and that's where we're going to utilize our synthetic data set as well to be able to depict for the models going forward what those extreme cases look like. What we found in the case of the teats and udder scores is when we were having our annotation team do these annotations, when you're looking at the graph that the CAA presents to the producers, there is a very clear definition of that upper polygon. But when you add fur to an animal and you combine that with computer vision engineers who know nothing about animals, it's very hard for them to annotate the upper polygon and be able to get it accurate enough. And so we're looking at other ways that we can get the same kind of accuracy out of the teat and udder models that we did not get